Good afternoon, everyone. Thank you very much for having us, and I think we are kind of having 20 or so people here. You're a true geek, I think, my machine. So let's begin. Today we would like to share with you some of our observations concerning internet traffic engineering and try to show you how LISP can try to make everything easier and simpler. And our presentation is mainly composed of the following 4 parts. In the first part, we like to show you some cases, some real problems that we've identified in doing internet traffic engineering and how BGP fails in handling them. In the second and third part, Luigi is going to give you a mini tutorial on LISP, on what it is and why it is much better than BGP in doing those problems. And finally, I invite you to join with me, and we are going to see together how we can use LISP to solve the problems that we've mentioned and presented in the first part. So here we go. Here comes the first case. It is a problem that we've identified in a real network, a real edge network. In this network, we can see on the topology graph to the left, it has 2 transits, A and B in this case. And we've deployed a probing system, real-time probing system to measure the performance, mainly delay of these 2 transits by forcing packets coming out and in via the same transit. And then the problem comes. We've identified some remote prefix or ASs that is talking to this local AS that we are observing. For example, the remote AS in this graph, whose BGP path comes out from transit B and comes in from transit A. No big deal, it's quite normal. The asymmetry of the BGP path in the internet is a well-known issue. So what then? So what if this kind of stuff has some performance issues? So let's look at the graph on to the right. That is a graph plotting the performance of these 3 passes. On bottom, we have the gray lines representing the round-trip time of the transit A. It is a quite good transit for this specific remote AS, kind of 10 milliseconds of delay, okay? And high above, we have the blue lines representing the performance, the delay of transit A. Sort of problematic, kind of 100 or so delay. And right in the middle, we have the orange lines representing the real performance, the real BGP path performance. What does all that mean to this specific remote AS that we are talking about? In detail, it means 80 milliseconds of performance drop. Just imagine if the local AS that we are observing is a kind of service provider and the remote AS in trouble is eyeball, and the site speed is taken into consideration when we rank the page. Quite catastrophic, I would say. And for the entire local AS that we are talking about, this kind of suboptimal incoming path problem represents a 314 gigabyte of incoming traffic alone. That is more than half of the total incoming traffic. So let's have a more tangible feel about how this problem it is. In this graph full of bubbles, actually, each bubble is a remote prefix who has a problem of suboptimal incoming passes, and the additional delay is more than 10 milliseconds. Only the prefix of more than 10 milliseconds delay are presented here. The additional delay here means the difference between the BGP performance and the minimum delay performance we can have with one of its transits. And each bubble here is a prefix, you know. And for example, their size is proportional to the incoming volume sent by this remote prefix in AS. And the red button high above is a reference button. It represents 1 gigabyte of incoming traffic. And just take a little dot high above there at the corner. Its best performance, theoretically, we can have is about 10 milliseconds, but its actual performance is more than 250 milliseconds. And you can say it is not important for being such small and so less traffic exchanged. But the case is that being such small, maybe it's a result of suffering from a large delay, get poorly ranked or whatever. And let's have a zoom look at the at the left bottom part of this graph to see how it looks where most part of the suboptimal traffic concentrates. Just imagine how good it can be if we are able to pull all those bubbles down to the ground to their optimal situation. Then comes the question, how could we possibly do this kind of thing with BGP alone? I think you all know how the BGP works, the techniques. You are true geeks, so I will pass this part. I will just go through this part really quickly. First, we have selective announcement. 2 versions. In the case that local AS can stop announcing its route to transit A, so all traffic will go into transit B. The problem is, first, we have connectivity issue. That is to say, we stop using transit A, what if transit B fails? And second, it is not granular. We are talking about some suboptimal remote prefixes, not the entire group. But this method is going to touch the entire group, not granular. And the second version, slightly better, which means that we can make local OS that we are observing announce more specific or prices prefix to transit B, so that the remote AS may prefer those more processed routes. Okay, get it? But again, the same problem, not granular, impacting the entire incoming traffic, and it gives rise to BGP table inflation. Just imagine in your BGP tables, all the entries are /24. Horrible. So what else do we have? We have AS prepending, that is to prepend itself several times in AS pass when announcing to transit A to make it not that attractive to remote ASs. And we can also do it via BGP community to make it more granular. That is to make transit A prepend itself several times when announcing the routes of local AS that we are observing to some of certain upstream ASs. The problem of AS prepending is that it is cheating about AS pass, its length, and it can't override the local preference setting in upstream ASs. And if the upstream ASs and the remoting ASs just prefer, for example, transit A, we can do nothing about it. So we have very unpredictable results of it. So in conclusion, all in all, in this kind of situation that we've seen, there's very limited BGP can do about it, and we have very limited control on the effects. And here comes the second case. It's about inbound traffic. And in this case, the network that we are observing, again, have 2 transit A and B, and their real-time traffic rate is presented in, by the blue area and the gray area. And both transits have the same CDR rate, which is a committed data rate, which is presented in orange. And for both traffic, we have also calculated their 95th percentile traffic rate, which is presented in those 2 lines. And we can see that for transit A, the 95th percentile rate is above the CDR rate, and there are times that its real-time traffic rate exceeds also the CDR rate. So what does it mean? What's the implication? What does this graph mean? And to me, it has multiple implications. It has multiple meanings. First, for real-time traffic rate, when it exceeds CDR, which means that you might lose the guarantee of service, your provider may drop your packets, possibly. If we go further in that direction, and the real-time traffic rate exceeds the interface rate, it's sure that you are going to lose packets. And with regard to 95th percentile traffic rate, you know well, it's about bidding stuff. You go past that, you pay more. But do we really have to pay more in this specific case? Let's just go back to the previous graph. We can see for real-time rate, there are times that there are pikes in transit A for incoming traffic. In the meantime, in transit B, we have plenty of capacity. And when talking about the 95th percentile traffic rate, we can see that the line for transit B is still high below the CDR rate. There's capacity there to dealing this amount of traffic, but we failed to do that. You can see that with transit A, we have already done kind of 4 times prepending, but it's not working. So again, here comes the question. How could we possibly deal with this kind of situation to move a part of inbound traffic from one transit to the other one? And again, solutions in BGP context. What can we do? We have selective announcement. But attention here, selective announcement is quite dangerous since we have seen before that it impacts entire incoming traffic, which means the chance is big that you might saturate transit B in this case as well to liberate transit A. Quite foolish, right? And AS prepending, we have seen the real results. It's not working, it's not effective, since we can do nothing on the decision, on our policies of remote ASs. So what can we do? Very limited with BGP. And here, with LISP, we shall see more about it.
Yeah, hi. So we will spend the next 10 minutes here following a crash course on LISP, or LISP 101 if you wish to use the American naming. So I will start, first of all, telling you why LISP, where it comes from. So this is the evolution of the number of prefixes that you find in the BGP routing table. It should be no surprise for you. I'm sure most of you already seen this. And for IPv4, this year, exactly the 13th of August, we went over 512K, meaning thousands of prefixes that we have in the routing table. So back a few years ago, around 2007, so the increase of the pace of the increasing prefixes was so fast that there was fear that very soon the BGP infrastructure will explode, right? So a bunch of people meet together and say, oh, we should do something about it, okay? And as usual, there are some people that say, yeah, this is a big problem. Others that say, you know, in a couple of years, routers will be even bigger. No big deal. Nothing will happen. Just as a proof, 13th of August this year, a few big ISPs in US had a few glitches just because, as I said, the number of prefixes went over the 512K kilo prefixes. So LISP was initially designed as a, let's say, a fix or a solution, something to avoid a situation like this. How does it work in the principle, all of this? It is a very simple principle. If we look at the structure of the internet today, okay, we have the tier 1 layer, so the bigger ISPs all peering together, okay, there are fuse. Then we have all the transit, and then we have this edge of the internet, all stub networks. So this is where the traffic goes and comes from, but never transits through these stubs, right? Akamai is there as well. 49,000 servers placed on the edge, right? 85% of the prefixes. Where it comes from, where are they come from, all these prefixes? If you look at the BGP numbers, you can go, you can find several sources. I took just Potaroo in order to do few rough calculations. We have today, actually 2 days ago, almost 49K active ASs in the internet. So basically we have one Akamai server per AS in the internet, right? And of this amount of ASs, we have almost 42,000 that are just origin ASs. So they just announce a prefix, and they are never in the middle of an IS path, okay? Traffic never goes through them, only comes from or goes to, never through, right? And roughly speaking, we have every AS announces on average 11 prefixes, which leads us to about 454K prefixes that come from the edge of the internet. Is this 85 here? Okay. Now, looking at these figures, do we really need, the question is, do we really need to use such architecture and put the edge and the core all together? What if we separate the core and the edge and we use a different routing infrastructure? or even a different routing model between the edge and the core. What if we do magic and we separate in the core, we just get rid of everything that is from the edge. The core just knows itself, meaning all the prefixes of the core itself. And we still use a push routing approach, meaning basically BGP. We announce prefixes, okay? About the edge, we isolated them from the core, and differently, we use a pull routing model. What it is? DNS. It's the same principle. We don't need to spread all the information all over the internet. It's a waste of time, energy, and resources. We just need to pick what we need at the exact moment that we need it. I come from Italy, from the south of Italy. My mother has a small ADSL connection, okay? I don't think my mother goes very often on websites that are based in Australia, okay? She doesn't speak English anyway. So why the provider of my mother needs to know a path to reach Auckland or Melbourne or Sydney? Why? It's a waste of resources. Now, we can separate everything, right? So imagine, what do we do if we have this separation? The same thing we do every time. We send packets. Let's say we have a source, and we want to send a packet in this split word, separate word. We have always an IP packet. We are able to route him inside the local AS until he reaches the boundary between the edge and the core, okay? Then let's say that we are able to ask an oracle what is the path inside the core in order to reach the other side, because the core is not aware about the edge. And the oracle has the right answer, as always. So we put some more information in the packet, and we are able to route the packet on the other side, right? There, we just can strip down what we don't need and route again our packet in the local AS. What we just saw is exactly what LISP does. LISP stands for Locator ID Separation Protocol. So the locator is something that is inside the core of the network of the internet, and the ID or identifier is at the edge. Just a matter of terminology. We are there. So the edge becomes endpoints, and so we use endpoints identifiers in order to route packets between the edges. In the center, we use routing locators. The addressing space is used to locate the identifiers in the internet topology. Okay, so the IP addresses of the border routers becomes routing locators. And our oracle is just a simple mapping system, because it has to map one addressing space to another addressing space. Let's take again the tour about the life of a packet in this world. So what we do is the end system, let's call it EID source, EIDS, wants to send a packet to EIDD. It's fetching content from Akamai. And what we do, we prepare a packet which use EID as a source and destination address. We route it inside the local AS, we reach the border router. Then we ask this oracle, the mapping system, so where is EIDD? Where is my destination? And the mapping system will reply with a very simple information, but very, very powerful. Okay? It's just an association between a prefix and the routers that through which we can reach him. Or, in other words, are the routers that locate the EID in the internet. Okay? And we can have a list of those, right? We take this information, we keep it locally in order to be used for further packets coming along. And then we are again able to route the packet on the other side. Okay? Now, the very important part is how to play with this association, how to play with the mappings, okay? Because this association between IP prefixes and routing locators can be done dynamically based on whatever metric that you want to choose. Could be traffic volume, local policies, packet drops, path quality, whatever you like. And there are means to control the way you can distribute this and how fast you can update all of this. Okay? It's just a matter of how dynamic and how much we can play with this association. And now Wenqin will show you a couple of examples about this.
So far so good. You all understand how that works. And now it is the exercise time. We will see how LISP can solve the problems that we present at the beginning. And just a simple reminder about the first case that we want to move the incoming traffic from transit A, who is a notorious one with bad performance, to transit B. How we can do with LISP? And the answer is quite simple. We are going to use a technique called kind of remote AS or prefix-specific mapping. The name is long, but the idea is quite simple. Here we see the local AS that we are observing, and it has two locators, one for transit A, the other for transit B, and itself has a EID prefix, which is same to his IP prefixes. What can we do? When the remote AS in question that sends a request for mapping that I want to send traffic to you, and the local AS can reply him with a list of locators, and we want the remote AS to use locator B. And we can simply tell him the only locator B to use. Done. But you are going to say there could be connectivity issues. What if transit B fails? Oh, sorry. But in this case, that we can attach to each locator a priority value. Like in the green label, we can say that, okay, please use locate B first. It is highly preferable. In case that it fails, you can switch to transit A. That is it. We've solved the first question. Piece of cake. Then how about the second one? Do you remember that in the second case that we want to move a part of the incoming traffic from transit A to transit B? How we can do that? We just need to slightly extend it a little bit the previous solution that we've seen. Previously, we have seen a specific or AS specific mapping, whatever. Now we need a group specific mapping. That is to say, we have to group all the remote prefixes into two groups. One for coming from the transit B, that is gray group, I will call it. And the other group is the blue group, are those prefixes who we wish that they come in from transit A. And give these corresponding labels, that is mappings, telling them which is the locator to use. And by grouping them, all those prefixes, we can also take performance issues into consideration, just as we've done in the first case. That is to say, if there's a remote prefix who works well by transit B, then we will put it in the group gray. And if there's another prefix who works well from transit A, then we put it in this group. And if there are prefixes there who serves equally well, we can use it to balancing the load on both transit C. And in one go, we solve the performance issue, we solve the load balancing issue. Easy. And we can even go further about load balancing the traffic between two endpoints in the network over several transits. Just imagine that you have inter-data center traffic that you want to balance those traffic on the several transits that you have paid money to. We know that it's not possible with BGP, but it's possible with LISP. Instead of giving a priority value to each locator that we send in the mapping, we give it a load balancing weight. The load balancing weight here can mean a lot of things physically. It can mean the real-time traffic rate. It can mean the volume. It can mean the flow count. But here we are just providing the possibility. And most of all, the important thing is that these solutions so far we have seen are not just beautiful ideas on paper. We are now having a platform, the infrastructure to implement them, to test them, and to evaluate them. And LISP Lab is now just a French project, and we believe that it is going to be global, and we are hoping that more of you to join us. And we are now cooperating with Border 6 to do implementation and the test and evaluation of the solutions so that to be optimal and reliable. Thank you very much for your attention. And we take questions, of course. Any questions? Yes.
So my question is, are you familiar with the explicit locator path solution?
Excuse me?
PCE?
LP, so explicit locator path
yes.
solution. So are you familiar?
Yes.
Have you done some implementations?
Oh.
I know this is still a draft on the IETF, but...
Is a draft, it's not an official working group draft, that one.
Okay.
So about the implementation, as far as I know, there are a couple of implementations that support that. In France, we are working on including that feature in OpenLISP, which is the open source implementation that we have. But we are not there yet. It's to come.
Any more?
Do you really see interest in LISP outside of Ciscalent and research guys like you? I mean, LISP is pretty much dead in IETF. Dean is out of Cisco, so.
Well, as a working group chair of the LISP working group, I can say that that's not actually true, that the working group is dead. I'm still alive. About the interest, I mean, there is a lot of the interest, so which goes beyond his initial design. The design was about BGP routing scalability. At the very end, his main application will be traffic engineering in the internet and in data centers. And that's where is the main application will be, and where there are I would say the main companies interested in. Okay, I think that there is another question maybe.
So maybe another question. You mentioned OpenLISP solution. This is open source, as I know.
Absolutely.
And
it's not the only one, by the way.
Yes, yes. And what is the status of? So I want to ask, when do you expect to have implementation of encapsulating router (RTR) in your implementation? This functionality.
That's a tough question because the real situation about the implementation is that OpenLISP itself has been designed around a FreeBSD kernel. Okay, so we want to go beyond that in order to have a multi-platform solution, and we know how to do it, and we are doing it. But we had to start to redesign the way we store the mappings, basically, in the temporary cache inside the kernel. So this design, in order to, in future, add this feature, slow down a little bit the implementation. So the forecast right now is that to have a new release with the features that were already there beginning next year, and then start to add all of the others, especially ELP.
Okay, thank you.